I don't think that we're energy limited as much as we're power limited. Um, I think that we're limited by both, but I think the power limitation is really the big thing with growing population electric vehicles. I think that our current grid capacity is like 1.1 terawatts for the US, something along that. So that's 1,100 gigawatts, 1,100 reactors. So if we were to add in another 300 reactors or something, because it oscillates massively, especially seasonally. Demand is huge, 20-30% shifts seasonally. So for all those peak times where we don't want people to freeze to death and everybody wants to make their coffee at the same time while watching the Super Bowl, in the middle of winter, we're going to have to increase the grid. Yeah, especially in electric vehicles make that harder.
Hey guys, Capital Cosm here. Before we start this video, I just want to let you know that I believe that we are on the cusp of a major uranium bull market. Now, these things don't happen every other week. The last uranium bull market peaked in 2007, the one before that in 1978. So when these things happen, you've got to take advantage of it. And how explosive are they? Well, you've all heard the stories of uranium skyrocketing from $10 to $20, all the way up to $150 in these uranium bull markets. Where will it go this time around? Well, we don't know. We'll see. But you've got to take advantage of the opportunity. What better way to do that than to leverage Justin Hune's Uranium Insider newsletter? You get access to his monthly newsletters, his webinars, his stock picks, his portfolio, all of that stuff. You get access to guests that you may not see on YouTube. You get access to having them ask questions that you may not see anywhere else. So I highly recommend, if you're going to take part in this uranium bull market, you check out Uranium Insider. The link is down in the description. Link is down in the description box below. Be sure to click the link. There's quarterly plans, there's annual plans. So if you're kind of tepid, you're kind of hesitant, you could always go with the quarterly plan. Kind of test things out, sample things out, see if you like it or not. But the way I see it, guys, you've got to pick the right stocks. A lot of these uranium companies are not going to make it to the other side. And Justin Hune's stock picks, his portfolio has outperformed URA, URNM. Now, and Justin Hune's uranium portfolio has outperformed the likes of URA by a significant margin. Since 2019, it's up 5x from where it started. So click the link down below, and we'll get started right now on the video. Thanks, guys. Hey guys, welcome to Capital Cosm. Today I have a special returning guest. It is Mr. Peter Devietien. Peter, thank you for coming on the show, my friend.
Yeah, man, great to be here. I appreciate being here again.
Yeah. Well, I appreciate you coming by. We've just had a hour-long pre-talk for this interview, so we've got the engines running. As always, guys, nothing on this podcast or videos which will be taken as financial advice. Neither Peter nor I are financial advisors, so please do your own due diligence. Peter, for those who may not have watched the first episode between you and I, quickly give us a summary of your background.
So bachelor's and master's degree in nuclear engineering. I was doing a PhD, but then I got a job in Canada to go build fusion reactors. So dropped out of the PhD. They gave me a master's degree, which was nice of them. Then did that for a few years, learned about startups, and then got into just trading a bit. And then I got enough money to essentially do my own startups from trading. So then I left that job. I'm now running like kind of a hedge fund, kind of a small family office. It's just me. I've had it floated to me to manage money for other people, but I'm kind of crazy, so I wanted to just do me. So that's my main source of income. And then I'm starting 2 startups on the side, one finance, one nuclear.
Yeah, so let's really hone in on the nuclear aspect. I know you're a big expert there when it comes to nuclear fusion. Explain to the audience what the difference is between fusion and fission. Fission is, what we have now. It's conventional nuclear power. But explain the value proposition of fusion there.
Right. Yeah. Oh, and then to preface this just a little bit, I worked in Canada, I worked for 7 years as a physicist, designing fusion reactors. So just to put that in.
Yeah,
Uh,
you're
so
not like me, who's just just stumbled into this sector, just trying to make
the,
sense of it.
this is
You have
not
to have
just
a formal
Wikipedia.
education.
Like I've spent 7 years building fusion reactors at a startup company as a physicist, doing computational physics. So yes, um, fission. Fission is what we've used for all the bombs. Fission is what we use for all the energy generation. And that takes the largest atom, which is the uranium atom. It's the largest naturally occurring atom, pretty much the largest. And then it splits it in half. It splits the nucleus in half. The nucleus is spinning around this is a good way to visualize it. It's spinning around extremely fast, and it's like kind of unstable and wobbly. And then one little neutron just has to go on and attach to it, and that's the straw on the camel's back, and then it splits apart, and that's splitting the atom. So that's fission. That's fission, and that's what we use for all of our current energy generation. Then fusion. Fusion is the opposite. It still uses the nuclear forces, and it's still all about the nuclei of the atoms. But fusion is when the two smallest nuclei, which are just protons, come together and fuse together. And when they do that, so actually the way we have it is I always do this. I haven't found a better way to do this. So proton, neutron, there's two there. When they collide so incredibly fast. They collide at the speed of light. The neutron breaks off at the speed of light. And that's where we gather the energy from for nuclear fusion. And nuclear fusion is what happens in the sun. That's how we get all of our energy from the sun.
Yeah, I
Yeah.
mean, so you get in the sun. In the case of the sun, you've got nuclear fusion fighting off gravity, and that's what that constant battle between fusion wanting to expand and gravity wanting to contract. That's what keeps the sun stable as a ball of I don't know, plasma, let's say, right?
Right. Yeah. Like that neutron that shoots off at the speed of light, the gravity will be so strong that it can actually bend that neutron and bring it back in. And then that neutron can go and hit other protons, which give it enough
Oh,
energy to create the process, to sustain the process.
I see. So
Yeah.
there's different approaches to nuclear fusion, from what I understand. You've got
Mhm.
magnetic confinement, and then you've got inertial confinement fusion. What is the difference between the two?
Yeah. So with magnetic confinement, sorry, I'm like a little bit sick. I just got to Buenos Aires a couple of days ago, so I'm a little bit sick, and it's been super hot here. So my voice is raspy.
And we just
That's
got
why.
done talking for like
Sorry
an
about that, guys.
hour beforehand, too.
Right. Yeah, we went over like all of modern history, which was epic. Like that's great. I'm impressed with how much history you know. Yeah, it's very, very rare that people know that
Likewise.
much. Um, thank you. Thank you. So with magnetic confinement, when you have a magnetic field and then you have a charged particle like a proton or like a proton and a neutron, if you have the magnetic field going this way, let's say into the screen, the charged particle will actually travel in a little ring inside the magnetic field. So that's how like cyclotrons work. Like they have like a external magnetic field, and then they have the protons go around in a bigger circle, kind of like the Large Hadron Collider ish. Um, so that is one way where we use the magnetic field to confine the particles. So you can have the particles be extremely high energy. Um, if you didn't have the magnetic field, the particles would just go and hit the wall and they would just be lost,
Right.
right? But you use the magnetic field to keep them all close to each other so they can run into each other and still fuse. So that's magnetic. And then it shows up in a whole bunch of different ways. There's tokamaks, there's stellarators, there's Z pinches, there's these are all different fusion reactor types, the fusion reactor approaches. And then each of those has like 20 different machines that they use to pursue those approaches. Then there's the one that I worked on, magnetic confinement, MTF, and sorry, magnetized target fusion, MTF. And I actually think that that's the best way. That's the startup in Canada. That I worked for General Fusion. I was a physicist in General Fusion in Canada, and I quit But I do think that that's the best approach. I had the option to go to France and do my PhD on ITER, which is the world's largest tokamak, but I chose Canada instead because I just think it was a better fusion reactor design. And then we can get into inertial next.
Yeah. Oh, why do you think that's a better design?
Mm.
And is that like is there a consensus in terms of design build for these fusion reactors, or is there still kind of like debate going on in terms of what's the best way to build these things out?
Yeah, there's still a lot of debate. If you were to get every single fusion scientist and put them in a room and have them vote, probably 85% of them would say that tokamaks are the way forward. And tokamak, do you want me to go over tokamaks?
Sure, go ahead.
Okay. Okay. Tokamaks are essentially so if you took, let's say that you just had rings of magnets, like in a line, right? Just rings, and then you just had plasma inside that ring, like the fusion plasma inside that ring. Now you just take that ring and then bend it into a circle, so it's like a big donut,
Right.
and then all the fusion happens inside the donut. That is a very controlled environment. We use like the world's most advanced superconducting magnets, and we use like I think like half of the world's superconducting magnets are used for tokamaks or something. Like it's crazy. So um so on the tokamak at MIT, they have 12 of these massive coils, like 15 feet tall magnetic coils going around the donut, and then those little rings, and they have a big bolt on it, and each bolt can hold a 747 because the magnetic pressure is so strong. So insanely strong magnets. It's very expensive. It's a great science experiment. We do get fusion out of it, but my guess would be it's like $80 per kilowatt hour or something. It's just insanely expensive. It's a science experiment. I don't think that we'll be able to, I'm just going to say 100. I don't think we'll be able to go down from $100 a kilowatt hour down to 10 cents per kilowatt hour or 5 cents or 3 cents. Um, but there are plenty of startups who think they can. And there's an MIT startup, there's a couple of startups that think that they can do that.
Gotcha. Well, you also alluded to inertial confinement as well. Kind of walk us through what that is.
Sure. Yeah. So the basic idea is how do you, so the sun is gravitational confinement. Like the gravity is so strong that it keeps the particles. Once the particles fuse, they have a massive amount of energy and they fly off into, the beyond. So they're gone. And then when that happens, you lose that energy. But what you need to have happen is you need that energy that's produced to go back and hit the cold fuel so that it then fuses and continues the reaction. That's what you need. That's why you need confinement. So
I see.
gravitational confinement, magnetic confinement, inertial confinement. The goal of all of them is confinement, is to not lose the energy from the reaction. So for inertial confinement, what they do is they just compress it. The main approach is you just compress it with a whole bunch of lasers until the fuel pellet is so small and the atoms are so close together that when a couple of them, I like using my hands for these things. I think I like
No,
to try
sure,
to give people a
illustrative.
little video, right? I try. So when one little fusion reaction happens and then it shoots off, hopefully it's high enough density that it hits another little piece of the cold fuel um, before it passes through all of it. And since it happens so quickly, those little fusion reaction pieces go off at the speed of light. All the other particles are so condensed down together that they're barely moving. Their inertia is high. I'm trying to get into inertia. So all the little fusion fuel particles are squished together, and then there's the reactions that are hitting all those little particles, but the only reason they have the opportunity to hit all those other little particles is because of the inertia of the cold fuel, because the cold fuel isn't moving and the fusion happens really fast. So that's still not clear. If you were to wait longer for okay, so The laser compresses all the fuel down in 1 billionth of 1 second. Let's say that we only did 1 millionth of 1 second. Let's say it took 1,000 times as long. Then the fuel would go there and then it would just all bounce off of itself and it would dissipate. And the fusion products wouldn't have the opportunity to trigger the cold fuel with more fusion. But since it's only 1/1 billionth of a second, that cold fuel doesn't have the opportunity to float away and bounce off of itself yet. So then all the fusion just happens with all those things that are like stuck in time through their inertia. And that's inertial confinement. That is so hard to explain.
No, I mean, you guys are gonna have to watch that over and over again to
I'm like sweating. Like that's inertial fusion, and it's using the inertia. So since it happens, it could almost be called like temporal fusion. Like since it just happens so fast, all the cold fuel doesn't have time to go away, so that it can just trigger the fusion products to hit all the cold fuel over and over again.
Right. So
That's inertial.
So inertial magnetic confinement, TC. What was the other one? TC.
MTF.
MTF.
Magnetic.
MTF, sorry.
Yeah.
So which
Magnetized
way?
target.
Which way do you think we'll end up going towards in building out these nuclear fusion reactors? What do you think will win out in the end, and why?
I think, yeah. Okay, so then this is actually like my nuclear startup. So this is great. This is great. Julia Pick. That's the name of it, by the way. The website's up, but like it was just me on Wix, so don't go to it yet. Like give me another year. Yeah, so I think that an MTF thing for space propulsion, I think that that's the best way forward. So a typical power plant, whether it's coal or nuclear or whatever, typical reactor is about 1 gigawatt, and that's a big one. That's like the maximum. There's plenty of them that are 300 megawatts. So we're kind of limited to 1 gigawatt for terrestrial generation, but Elon's BFR that it's sorry the BFR is his huge Mars ship down in Texas. All of SpaceX's revenue comes from Florida when they just do low Earth orbit and they put satellites into orbit. Then they have the Mars ship over in Texas, which can hold 100 people. It's massive. It looks like a skyscraper. Two-stage, completely developed by SpaceX. That one is the largest, most powerful rocket in human history. And that one is roughly about 100 gigawatts, roughly. That's like the energy output. And with fusion, the larger it is, the easier it is. And that's part of the reason why people like tokamaks is because it's easy to make them large. And then, so for a nuclear bomb, so the largest thing is a sun, a star. If you go big enough, fusion just happens naturally. Jupiter is not big enough. Jupiter is quite big, but it is still not big enough.
It's a failed star.
So you need to go bigger than Jupiter. Yeah. It didn't make it. It couldn't ignite. It couldn't contain. The gravity wasn't strong enough to have enough confinement
to make
dwarf, the reaction. Right? Oh, is it?
I think that's what it's called.
I didn't know that.
The brown dwarf, I believe.
I don't know. I hope so, because that's awesome. Like that'd be cool. I don't know. So go super big. It happens naturally. Then the next one down is a fusion nuclear weapon, of which we've detonated many. So that's still very big. You know, that's in the terawatts, or like probably way more than that. Way orders of magnitude more than that. But we obviously can't be doing that all the time, right? So then the challenge is to get fusion small enough. And I think that the next small thing is space propulsion, like going to Mars. Like going to Mars in like 1 or 2 weeks as opposed to like 4 months. And then after that, I think that we'll make it smaller and smaller and smaller from there. Make smaller and smaller ships, and then we'll be able to make it on Earth. And using MTF. Yeah. Yeah. I'll let you respond, then I can get into MTF.
Yeah. No. I'm pretty much just at a loss for words. I mean, so you essentially building out like a miniature sun. Is that what essentially it is?
Every single fusion device creates a mini star and attempts to extract the energy from it.
Wow. Didn't China build
Yeah.
something along those lines several years back?
Yeah, China is, doing great on the fusion front. They have I went to East. East is the largest tokamak in Asia. It's one of the largest in the world. And they're doing great stuff and they build all of it there. They build it all on site. They're building a lot of good stuff. So I hope we get it first because they're
Yeah,
they're
they're
serious
a little bit ahead of the
competitors.
game though. They've got thorium reactors already built out, don't they?
I don't know about China and thorium. I don't know. I haven't heard anything on that. I know that they're going huge on nuclear. Like
Yeah,
they're
like
going
100
they
new nuclear reactors to be built in the next
right.
next 10 years or so.
Yeah, I think that they're going to build more in the next 20 years than we have total.
Mm-hmm.
And that's just ignoring their existing fleet, which I'm actually not sure how big their existing fleet is, but they have quite a bit. Um, when I was doing my PhD, I was taking the classes. More than half the students were Chinese. In Indiana, Purdue, which is not known for its diversity, right? Um, when the class was over, all the students would stand up and everybody would begin talking, and it would be Mandarin. It wasn't English. Uh, the English kids just kind of like, put their head down and walked out. They were the minority in nuclear engineering.
Yeah. Well, what was the next model you're going to cover?
MTF.
MTF.
MTF. So yeah, this is the one that General Fusion uses up in Canada, and there's been a whole bunch. There's a huge lineage of MTF, um, and it's essentially kind of like halfway between magnetic confinement and inertial confinement, and that's part of the reason why I like it so much. So you use a magnetic field to confine it, and you keep the particles inside. The particles are traveling around in their little circles, but then you also compress to just do both. You have the magnetic confinement, and
Hey
then you
Peter.
get the increase in
Hey
density.
Peter. You cut off for like 5 seconds. Can you rewind?
Oh no.
Are we cutting off?
Okay, sure. I'll
Yeah.
rewind.
Yeah.
Yeah, you just cut out, and then I realized that my Argentinian internet connection probably just didn't
I
serve
think it's
us
actually
well.
from me. But yeah, let's go ahead and try
Oh,
and power
really?
through this.
Okay. Yeah, sure, sure. MTF, magnetized target fusion. You have the target because you're compressing the target, but then the target itself is magnetized. So you actually take a very similar magnetic structure. Often, it'll be in the shape of a donut. Um, Magnets just naturally like to go in the shape of a donut. Like the magnetic field of every planet is in a torus. It's in the
Yeah.
shape of a donut. Um, and so you're kind of just limited because there's no magnetic monopoles, otherwise like you can have like a proton and then the electric field goes out in all directions equally. That's a monopole.
Hmm.
So you can have that for the electric field, but you can't really do it for the magnetic field. Um,
What
so
about what about the
yeah,
fact that electromagnetism, the electricity and magnetism are two sides of the same coin, right? They're one of the four forces by virtue of electromagnetism.
totally. If you have a proton just sitting there in space, not moving, then it has an electric field. And then if you start to move that proton, then it creates a magnetic field.
Mm, okay.
So they're very a magnetic
So
field is
magnetism is
essentially
like
just a moving electric field.
okay, yeah, got it.
Yeah. Yeah. Sorry, I'm always so tempted to finish that sentence,
Yeah,
like that's yeah. It's a like the equation for yeah, you only get a magnetic field when you have current, and current is moving charge. Otherwise, you don't have any magnetic
gotcha.
field.
Yeah, I'm a
Yeah,
mathematician, so I deal in the theoretical. Like, I mean, the practical side of mathematics isn't my strength, but this is
right.
great stuff.
Oh, well, it's great. If you know math, you can learn physics in like 15 minutes. Like that's the math is the hard part. It's physics is just like math plus stories
Right.
and little movies in your
It's just
head.
applied math.
That's all it is. Yeah, it's just applied math. Yeah, math is great. We need way more math majors. Um, so you create essentially a tokamak plasma, and then at the same time you have the device be able to compress the plasma very, very quickly. So you'll take something the size of a small bedroom. You'll get a plasma the size of a small bedroom, like a tokamak plasma, and then you need to build a machine that can compress that thing the size of the room in 1/1000th of a second or faster. And that's what General Fusion's trying to do. That's what a few other companies are trying to do, and that's MTF.
I see. So we've covered nuclear fusion by way of energy production. Is there like a nuclear weapon that can be produced through nuclear fusion in much the same way that splitting the atom does with like a nuclear bomb?
Totally. Yes. And we've already done it. We've already done
Oh,
it
okay.
plenty of times. Yeah, we have fusion. So uh Hiroshima and Nagasaki, those were pure fission. Those were solely plutonium. Um and that I forget, maybe one of them was uranium. I forget. You can make nuclear weapons with uranium or plutonium. Plutonium's just way easier. You don't need as much of it. The absorption cross section is higher, so it absorbs the neutrons easier. So you only need like 1/5 as much plutonium or something, so you can make a much smaller bomb that has the same power. Um, and then very did you see Oppenheimer?
Yeah.
Okay, okay. Do you know Edward Teller? He was kind of like the young, like stronger guy who was very forceful about doing fusion.
In the
Did
movie?
Yeah, in the movie.
I don't
He
remember.
was the one Oppenheimer. He like kind of like stormed out a couple of times, and Oppenheimer had like a heart to heart with him.
Oh, yeah, yeah. Yeah. That guy.
Yeah, okay. It's hard. It's esoteric. So he's the father of the hydrogen bomb. Um,
Gotcha.
he started Livermore National Lab, Edward Teller, and he pushed for the fusion bomb. And a fusion bomb is roughly 1,000 times as powerful as a regular nuclear bomb, a
Oh, wow.
regular fission bomb. Yeah. So with a fission bomb, you can take out small cities, and with a fusion bomb, you can take out small states. Um, so
What was
yeah,
the
they're
it
they're a big deal.
was the Tsar Bomba? Was that a fission bomb?
Yes, that was sorry, that was a fusion bomb.
That was a fusion
Yeah,
bomb. Okay.
Sarbomba was a fusion bomb.
Gotcha.
That was like uh 50 megatons, I think.
Yeah.
Um
It,
and
it was so they
yeah,
actually had to scale it down. It was originally a 100 megaton bomb, but they had to scale it down they gave enough time for the pilot who dropped the bomb
amazing.
to actually get away before they got incinerated. And
Yeah.
it reverberated around the globe for 3 consecutive times.
Yeah. Yeah, you get into planet shaping. There's theoretically you could just add more and more fusion fuel, and then you could make it arbitrarily large. But we have the only way that we have been able to create a fusion nuclear weapon is by detonating it using a fission nuclear weapon. So we have to use the fission in order to make the compression intense enough and add in enough energy for the fusion to happen. So if we were to do fusion, let's say that we give Pakistan and every unstable country just all over the world, all the Middle East, everything, fusion nuclear reactors, but they had zero fission fuel, they could not make a nuclear weapon. You have to have you have to have all the equipment that you need to make a fission nuclear bomb in order to make a fusion nuclear bomb. So
Gotcha.
there's actually not the proliferation risk, which is one of the big advantages of fusion.
Yeah. So it's an escalatory risk. So you gotta make the fission before you can make the fusion.
Right. Yeah. You got to have both. If you only have fusion, you can't have a nuclear weapon. And then it's, clean energy forever for fusion if we're able to figure it out.
Is there a limit on how big these bombs could get?
I don't really think
Because I've
so.
heard like
I,
I
I
mean I've heard like the Satan missile that Russia has that supposedly can, which is like a composite missile, right? It holds like multiple 100 megaton bombs, and it could
Yeah.
foreseeably take out something the size of France or Texas.
I mean, like, if you were to take a bomb the size of Costco and like put it, 200, put it 100 miles down, I wouldn't be surprised if you could create another little moon. Just blow off a chunk of the planet
Wow.
and create a little moon. Like you probably could.
Wow. That's
Yeah.
hope we never get to see the light of day when it comes to those
Oh,
bombs. That'd
good
be
luck getting that
I
much
hate looking
tritium, you know.
looking at that Tsar Bomba footage back in the 60s or
Mm.
70s. I mean, it's so chilling. And that's
It is.
technology from 40 to 50 years ago.
Yeah. Yeah. And I mean, like, to the uninitiated, like I understand why people were against nuclear power. Like I get it. I think that it was extremely misguided and extremely damaging. I think it was a horrific, I think it was one of the worst things that's happened to our species in the last 200 years was killing nuclear power. Um, but if you don't understand how the world works
Yeah.
and you just see like big bomb, I understand how people get scared, like it's the animal mind in me understands,
Yeah.
the reaction.
Yeah. But I think we're turning I don't think we have a choice in the matter anymore. Yeah, nuclear is going to be the uh energy source to take us to the future, right? I
Yeah.
mean, you've got things like is fusion the most dense energy source? I guess compared to things like
Yeah.
geothermal. Like I've heard geothermal was
Yeah.
also pretty much up there as well. Like how does nuclear fusion compare to everything else? I know it's like 10
Yeah.
times more dense than fission.
Correct.
Yeah.
Yeah. It's ten times more dense per unit of mass of
Mm-hmm.
the fuel. It's 10 times as dense. Um, so yeah, in general, nuclear is just a whole different ballpark. Nuclear is orders of magnitude more dense than anything else, and I assume it's the same with geothermal. Um, Geothermal is kind of interesting though because there's no fuel, so you're kind of just putting it against something hot, so that's
Yeah.
kind of hard to compare. Um, but for the fuel consuming approaches, or actually, you know what? Probably a better way to look at it is just total mass consumed because eventually the reactor breaks, right? Um, so actually, probably in just total mass consumed of just operating the reactor, nuclear is probably like way more than geothermal in that respect.
So can we leverage an increase in electricity output through even nuclear fission? Like if we just begin adopting more nuclear fission onto our electricity grid while keeping the same amount of, let's say electrical wiring on the grid,
Mm.
do we need to increase capacity to actually be able to pull in all that energy, or how does that
I
work?
I think so, especially with electric vehicles coming online. They just consume I don't think that we're energy limited as much as we're power limited. Um, I think that we're limited by both. But I think the power limitation is really the big thing with growing population electric vehicles. I think that our current grid capacity is like 1.1 terawatts for the US, something along that. So that's 1100 gigawatts, 1100 reactors. So if we were to add in another 300 reactors or something, because it oscillates massively, especially seasonally. Demand is huge, 20-30% shifts seasonally. Um, so for all those peak times where we don't want people to freeze to death and everybody wants to make their coffee at the same time while watching the Super Bowl, like yeah, in the middle of winter, we're going to have to increase the grid. Yeah, especially in electric vehicles make that harder.
How much of a tall order is that?
I should know better than I do. I actually just don't know. It seems very expensive.
Yeah,
It
because I
seems
see a
very
lot of
expensive.
I see a lot of people pushing, myself included, pushing things like nuclear energy. It's the solution to a lot of our problems. It's way more dense than natural gas, coal, etc. It's cleaner, blah blah blah. But people often are absent of the issue with the capacity of the electrical grid. So how are you going to increase? You can't just increase output while having the same electrical line, power line grid the way it is now. You have to create more
Right.
power lines, right?
100%. I mean, if we were to just all of a sudden consume twice as much water throughout the country, we would have to redo all the sewage and plumbing systems.
Mm-hmm.
We would have to double their capacity. And I think that that's quite expensive. Yeah, I think it's quite expensive. And there'd have to be smart ways to try to increase that capacity.
Are there any other applications for nuclear fusion outside of the electrical grid?
Uh, yeah. So
Aside
people
from
use
making
it as a
bombs
neutron
too.
source.
What's that?
Yeah, right. So bombs, people use it as a neutron source. So if you want to create exotic isotopes, like for medical imaging, or just any sort of imaging, like if you uh, so an X-ray machine uses photons to pass through the object, and then the object absorbs some photons, and then you just measure what got absorbed, and then you get a picture, you get a shadow. You can do the exact same thing with neutrons. You can have like a neutron X-ray, so to speak, and then you can just shine a whole bunch of neutrons on an object, and then the object absorbs and the atoms that absorb neutrons are the exact opposite atoms that absorb photons. Um,
Hmm.
if
So it's
if
kind of like
I may have said
MRI.
that
Is
too quickly.
that kind of like MRI?
So kind MRI is closer to an X-ray, but it's kind of its own beast. MRIs use magnetic fields to get the object to produce photons, which you then measure the shadows of. That's how MRIs work. X-rays produce the photons directly. So you can use neutrons to detect all sorts of things like gunpowder. Neutrons will detect gunpowder. They'll detect nuclear materials much better than X-rays ever would, or an MRI.
Gotcha.
So you can use it for general detection. And then, of course, space propulsion. Um,
Oh,
once, yeah, I think that that's the big one.
well, I mean,
I think that, yeah,
we already
yeah,
use it for submersive propulsion, right? With like nuclear powered submarines.
we use fission for that. We
Yeah.
use
Okay.
fission for
Fission.
that. Yeah, yeah, yeah. Um, and fission's great. I mean, fission's incredible for propulsion. I think that once we have fusion propulsion, then we will unlock asteroid mining. Then that becomes trivial, because you'll have a machine that has enough energy to drag an asteroid between planet to planet on the order of days. Yeah, so I think that you have to have fusion first. Like if I were an alien and I had like 300 planets to visit, I would skip any planet that didn't have fusion yet. I'd be like, well, I don't care about their philosophy. Everybody probably has
Yeah. For
same
sure.
kind of philosophy. If they haven't gotten fusion yet, they're not that great, Like
Yeah.
um,
Screw these guys.
GDP potential, yeah, yeah. GDP potential goes up like quasi infinitely once you have fusion.
Well, apparently are we, how far off are we from adopting fusion at a scale that's actually relevant?
That's such a great question. That's such a great question. And it's so easy for people to be mad at me for anything that I say in any direction on this. Which that's okay.
People
There's
in the comment section, cast your insults directly at Peter now.
yeah, at Peter Devietien. Yeah, send him, send him. Um, there's a handful of companies that are saying that they're gonna have a prototype that will prove that they can produce fusion within the next 10 years. There's a handful of companies saying that they'll be able to do that. I have my own fusion startup company. I personally don't think that any of them I think that some of them are incredible. I think that some of those companies are incredibly cool. I think that they're going to push I think they're going to set 15 world records in a row. I think that a lot of them are super cool. Um, but I don't think that we've found the design yet that's like the grand slam. I don't think we found the one that is good enough technically and profitable enough. I don't think we found that intersection yet. Um, so yeah, that's my startup is trying to find that design.
Gotcha.
Yeah.
Well, best of luck there. Peter, thank you
Thank
so
you.
much for coming on the show. Really enjoyed this second
Yeah.
time around. We'll have you again on for a third time, if nothing else, just for our pre-show talk. It's really enjoyable uh, podcast here. Got a lot of great insights when it comes to the inner machinations of fusion. What distinguishes fusion from any other energy source out there? People in the comments section, let me know what you think. Are you as excited for fusion as Peter is? If so, let me know. If not, also let me know. I'll try to respond to every single comment down in the comment section down below. Also, like the video if you enjoyed this kind of content. Subscribe to the channel so we can get more guests like Peter on the show. And with that said, Peter, any concluding thoughts? And where can we find you?
Yeah, no, thank you so much for having me on. This is hugely refreshing. I've just been thinking about finance 24/7 for a long time. So it's like, thank God I go back to Fusion. It's more interesting in my mind. But yeah. I'm mostly on Twitter. At Peter Devietien. That's kind of a long handle. So could you put that like in the
We'll
show
have it.
notes?
Yeah, we'll
Yeah,
have it on
yeah,
screen too.
yeah.
We'll have it on screen.
And then that's just my full name, just Peter Devidian. And then yeah, final thoughts. Just yeah, thanks for having me on. It's great to be here and great to talk about fusion.
Likewise. All right, guys. Well, if you enjoyed this podcast, video, whatever you want to call it, be sure to give it a like, and I will see you in the next episode. Bye, y'all.